Well, hello and welcome to the 10th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. Without further delay, let me recall what we were doing. We were in the middle of deriving, proving a theorem. Let me remind you what the theorem was about. So, we have two behaviors, behavior B, which is given by kernel of R psi, and we also have behavior B tilde given by the kernel of R tilde psi, right. We assume that these are both are such that they are square with non-zero determinant, because that is the situation that we have seen so far. Both R psi and R tilde psi are of the same size and square matrices, and both of their determinants are non-zero. We do not know that yet, not equal to 0, and determinant R tilde psi also not equal to 0. We assume that B is equal to B tilde. The question is, what can we say about the relation between R and R tilde psi, right? Okay. So, we said we are going to prove this by induction on the number of independent variables, number of dependent variables, induction on the number G. The base case G is equal to 1, let me write that down, that is the base case. And what is that? G is equal to 1. For that, it's a G equal to 1 means that it's a scalar system. In that case, R psi is just a polynomial, right, because G is 1 and so is R tilde psi. So, they are just polynomials, and in that case we have already seen that one must be, the two are just constant multiples of each other. That means there exists a number u, which is a real number, non-zero, such that R tilde psi is equal to u times R psi, right. We have seen that the two modules are the same. Okay. What happens in the general case, and that is the inductive step, right. What do we mean by the inductive step? Inductive step, as the principle of induction goes, inductive step means that we assume truth of the theorem, for the case G minus 1, show that show truth of the theorem, or rather derive truth for G, right. That is the inductive step. Now, how do we go about doing this? So, for that, what we are going to do is we are going to assume that R psi is in this form, that is without loss of generality, because we have already seen that matrices can be brought to the upper triangular form by a unimodular row operation, by a series of unimodular row operations, which means these are unimodularly equivalent, right. So, therefore, we may assume without loss of generality that we have already done that process and brought these matrices into this particular form. Now, in this scenario, suppose we take W1 and 0, where W1 is a C infinity trajectory of size G minus 1, such that W1 0 is an element of B. This implies R11 xi w1 is equal to 0, right. So, for all w1 which is in the kernel of R11, such w1 zeros are always part of B, correct. Likewise, if I take w1 tilde 0, okay, sure, no problem. So, this is in B, or rather we start with this, we take this and we take and we do the following. We do this and suppose w1 belongs to kernel of R11 xi. This implies w10 is in B, right, but B is equal to B tilde, that was our assumption to start with. This implies w10 belongs to B tilde as well. This implies R11 tilde xi w1 is equal to 0, which then means, notice carefully, that this means kernel of R11 xi is contained in the kernel of R11 tilde xi, right. Likewise, just following the, just reversing the logic, w10 let me call it w1 tilde 0 with w1 tilde in kernel of R11 tilde xi would imply w1 tilde 0 is in B tilde, but that is equal to B by our very assumption. This implies w1 tilde belongs to kernel of R11 xi, which then means that kernel of R11 tilde xi is contained in kernel of R11 xi. Now, what does that mean? What we have essentially shown is that the two kernels are equal, one is contained in the other. So, we in fact have equality of the two kernels, great, no. Now, once we have equality of these two kernels, and we remember that these matrices are smaller sized matrices, this matrix is size G cross G, yeah, tilde R11 xi, both of these are size less, sorry, this is G minus 1, this is G minus 1 times G minus 1, smaller size matrices. Because they are smaller size matrices, by our inductive hypothesis that the theorem must be true for G minus 1, by inductive hypothesis, this implies there exists a unimodular matrix U xi of size R G minus 1 times G minus 1 xi such that now R11 tilde xi must be equal to U xi R11 xi, perfect. So, this is what we have as far as this R11 block is concerned, this G minus 1 by G minus 1 block is concerned. Now, that is not enough, right, we need more, we need to show R tilde is equal to some unimodular matrix times R. How do we prove that? Now, let us come back to our the R xi matrix. Yeah, what was R xi? R xi was R11 xi, R12 xi, which is just a vector 0, R22 xi. Okay. Now, suppose some w1 w2, where w2 is a scalar and w1 is a G minus 1 size vector. So, w1 is, I do not know yet what they are, but that is it, that is we partition w into w1 and w2, which looks like this. So, that w2 is just a scalar. Now, suppose this guy is in B. What can we say about that then? Notice that this means R22 xi W2 is equal to 0. That means W2 must necessarily be in the kernel of R22 xi. Okay? Now, further it also means now how do I get the corresponding W1? Notice carefully, this is very important for us. R11 xi W1 must then be equal to minus R12 xi W2, right? Can I get a W1 that satisfies this equation with this particular W2? Namely, let me call this as W2 hat. To distinguish that W2 hat is this particular trajectory that we have chosen to be in kernel of R22. Can we have a W1 that satisfies this? The answer is yes. You see, because R11 is a square matrix, right, and because we are assuming R has non-zero determinant, determinant of R11 must also be non-zero. Look at this, yeah. This is a block upper triangular structure. The determinant is determinant of R11 times R22. Because the determinant is non-zero, it follows that the determinant of R11 must also be non-zero. Because the determinant is non-zero, now notice that W2 can be gotten by looking at this R12 xi and R11 inverse xi. What is this? This is a rational function matrix of size g minus 1. It is a vector. So, it is a rational function, it is a vector of rational functions. And then solving for W1, this requires us to just solve this system of, so W11 is equal to, the first entry of this guy, right, the first entry which is the rational function multiplying W2 hat, acting on W2 hat, and we already know how to solve this. We know this through the convolution integral, right, the particular solution that we had obtained last time. In the last lecture, go back to your last lecture and find out how to obtain these. You just have to do this partial fraction expansion and so on. Okay, right. So, we in fact have solutions. So, the point that I am trying to make here is that for every W2 hat, let me rewrite, for every W2 in the kernel of R22 xi, there exists a W1 such that W1, W2 together is in the kernel of R xi. Okay? Now, what does that mean? Now, this means this W1 and W2 which is in B must also be in B tilde, because B and B tilde are equal, right. But that means R11 tilde xi, R12 tilde xi 0, R22 tilde xi, W1 W2 must be equal to 0, which then means R22 tilde xi W2 is equal to 0. What does that mean? That means kernel of, remember where did W2 come from? We started with assuming that W2 satisfies this equation. Yeah. So, W2 hat was in the kernel of R22. So, this essentially means kernel of R22 xi is contained in the kernel of R22 tilde xi. Just reverse the chain of arguments and you will have kernel of R22 tilde xi to be contained in kernel of R22 xi, which essentially means that the two kernels are equal. The two kernels are equal. Lovely. Just follow the chain of arguments clearly. We start with this and say that suppose I take something in this kernel. We show that for everything in that kernel there is a corresponding W1, so that together W1 W2 is in the kernel of this big matrix R. But the kernel of this big matrix R is the same as the kernel of big matrix R tilde. So therefore, the same W1 W2 must be in the kernel of R tilde, and if they are in the kernel of R tilde, in particular W2 must be in the kernel of R22 tilde, which means kernel of R22 xi is contained in our kernel of R22 tilde xi. Reversing the chain of the arguments, we have the converse. So therefore, the two are equal. But now these are scalar, right? These are scalar equations. Therefore, I mean R22 xi is just a polynomial, R22 tilde is just a polynomial, and their kernels are equal. So what we have seen already in the last lecture, that this means the two must be related to each other by a constant multiple. So R22 xi must be equal to some alpha times R22 xi, where alpha is a non-zero real number. Great, we are almost there. We are almost there. We have taken care of this. So remember the form that we had assumed for R and R tilde, right? What was the case? We had assumed, yes, these are the forms. We have found out relation between this and this. Now we have also found a relation between this and this. What remains is this guy, this block. It's a vector. What happens to R1 vector? How are R1 vector and R12 vector and R12 tilde vector related? Okay. Notice, what do we have? We have now, okay, let W2 belong to the kernel of R22 like before, and we have seen that for every such W2 in this kernel there will be a corresponding solution W1. So there exists a W1 which is a C infinity function, right, such that this is a very crucial step. Clear it if it's not clear to you. Go back to the go back in this video and clear out that this is indeed true. Satisfy yourself. Now W1, there is this W1 such that W1 W2 together is in the behavior, which means they together satisfy the equation R11 xi, R12 xi, 0 R22 xi. Okay, this is equal to 0. Now we look at this guy. This means R11 xi times W1 plus R12 xi times W2 is equal to 0. I just multiply this by u xi, okay, plus u xi. See, the multiplication is compatible because it is a square G minus 1 by G minus 1 matrix, and this is a G minus 1 size vector. So the vector matrix vector multiplication makes sense. This is my equation number 1. But you see, this also implies, because B and B tilde are equal, R11 tilde xi, R12 tilde xi, 0, R22 tilde xi, W1 W2 must be equal to 0. I look at the first equation, that is R11 tilde xi W1 plus R12 tilde xi W2 must be equal to 0. But what is R11 tilde? We have already proven that R11 tilde is just u xi times R11. This is my equation number 2. I subtract one from the other. Yeah, I subtract 2 from 1. When I subtract 2 from 1, this guy goes away. What are we left with? U xi R12 xi minus R12 tilde xi acting on W2 must be equal to 0. Check. That is what I get. This minus this equal to 0. And that is true for what? That is true for all W2 in the kernel of R22, right. Now, how many equations are there? G minus 1 such equations are there. For each of those G minus 1, listen very carefully, for each of those G minus 1 equations, what does this say? It says that if W2 belongs to this kernel, that means if R22 xi times W2 equal to 0, that implies U xi R12 xi minus R12 tilde xi W must also be equal, W2 must also be equal to 0. How many equations are there? G minus 1 equations. For each of those guys must be 0 whenever this is true. So, if I look at the individual kernels of these G minus 1 entries, each of those G minus 1 kernels contains the kernel of R22. Now, what does that mean? For a scalar system, all of them are scalar, right? These G minus 1 individually are scalar systems. W2 is a scalar trajectory. So, for that W2 scalar trajectory, if it is in the kernel of R22, it is also in the kernel of each of these guys, right. Remember, we have seen that kernel of P contained in kernel of Q implies P must divide Q, which means each of these vector entries must be divisible by our R22. What does that mean? That means there exists Q xi, or let me call it, that means there exists U xi, yeah, which is a vector of size G minus 1, vector of polynomial size G minus 1 such that U, capital U xi, R1 to xi minus R2 to xi, R2 to tilde xi, yeah, is equal to U xi times R2 to xi, okay, or in other words, this is plus, right. Oh, sorry, there is a minus. There is a minus, which then implies that, let me check whether I did it correctly. Sorry, this is R12, this is R1 to tilde, yeah, now it is correct, yes, right, okay. So, that means, R1 to tilde xi is equal to U xi R1 to xi minus U xi R2 to xi. Let us check the sizes. This is G minus 1 size vector. This also is a G minus 1 size vector. This is a scalar. This is fine. Okay. So, now let us see what we have. We have R tilde xi given by R11 tilde xi, then R1 to tilde xi, 0 R22 tilde xi. That is R tilde xi, right. What have we proven? At the moment the behaviors are equal, we have this to be equal to, we have R11 xi here, R12 xi here, 0 and R22 xi here, right. Now, this means first equation says that R11 tilde, let us put a 0 here. What does that mean? Let me write this down, then we verify U xi and this is alpha, right. Okay. The product, this row times this column is u xi r11. Let me write down the product. Let me get rid of the xi so that it is easier, let us cumbersome. This is u xi times r11. What is the second entry? The second entry is u times r12 okay, let me put a minus, there should be a minus here, minus u times r22. Okay. That is the second entry. What is this entry? This entry is 0, 0, this is 0 again, and this is alpha times r22. Now check, is this indeed true? Yes, we have already proven r11 tilde is equal to u times r11. So this is checked out. R12 tilde, just now we have proven R12 tilde is equal to u times R12 minus small u times R22. Yeah, that is what it is. And this is anyway 0, and R22 tilde is alpha times R22, that also checks out. So essentially what have we proven? We have proven R tilde xi is equal to u xi small u xi 0 alpha times R xi. Is this matrix unimodular? Of course, you bet, because this is a block upper triangular matrix. This is unimodular. This is a non-zero scalar. So this also must be unimodular, because the determinant of this guy must then be equal to determinant of u, which is a constant, times alpha, which is also a non-zero constant. So this is a non-zero constant. So this big matrix also is unimodular. You see what we have proven? Fantastic. What have we proven? That as long as we are interested in this in C infinity trajectories for square system of equations, square system of ordinary differential, linear ordinary differential equations with constant coefficients, two behaviors are equal if and only if the modules that their rows span, they are equal. Yeah. So B is equal to B tilde implies now R is equal to R tilde. The other direction we had already proven, so we have an if and only if condition now, right. So let me just write it down as if and only if. The only catch was that we had assumed, under the assumption that R xi and R tilde xi both were square G by G size matrices. Okay. There is a special name for such systems which we have not mentioned yet. Such systems are called autonomous systems. It will become clearer why they are called autonomous as we move along, when we learn about elimination and inputs and outputs of systems and so on. They are called autonomous systems. For now, it suffices to say that these are autonomous systems because if you look at the form of their solution, if the initial conditions are specified, then the solutions get specified uniquely, right. There is no input per se, there is no freedom in their solutions. In fact, it so happens that their kernels are finite dimensional vector spaces, you see, because they are finite direct sums of finite dimensional vector spaces. Remember, long back we had, in 2 lectures back, we had parameterized the solutions of these kind of equations. Yeah, and they are finite, they were direct sum of these components. Remember, kernel of xi plus lambda to the power mu. This is a finite dimensional vector space, and the overall solution is a linear combination of these guys for scalar. And then when you go to the vector case, it's just back substitution, and each time you get such finite dimensional solutions. So, therefore, overall it is a finite dimensional system. So, autonomous systems are finite dimensional, and for autonomous systems, behaviors being equal is equivalent to the equation modules being equal. What happens when the systems are not autonomous? In other words, when the systems are such that their kernel representation matrices are no longer square, what happens then? In that case, we do the following. Suppose we start with a behavior which is kernel of R xi, right? We assume that R xi is full row rank, yeah, is assumed to be full row rank. How can we do that? Remember, do unimodular row operations and bring it to upper triangular form, get rid of all the 0 rows, you make it full row rank. If it is full row rank, then I can do the following. I can possibly, after rearranging the variables, rearranging the columns, after possibly permuting the columns, we can bring R xi to be of this form, P xi minus Q xi, where P is size G, this is also size G, remember full row rank, and this is Q minus G, so that the determinant of P xi is non-zero. Remember that it may not be possible to do so unless we permute the columns. Now, what does permuting mean? Permuting of the columns really mean the following. You see, if you have variables W1, W2, two variables and two such polynomials, when you permute, this comes here, this comes here, that essentially means that you are rearranging W1 and W2, you are rearranging the variables as well. So, that is what rearranging the variables is not a big deal, is not it? If you have several variables, which one you call as W1, which one you call as W2, and which one you call W3, and so on, that is your choice, right. So, you are just making a making a choice again about naming these variables, numbering these variables. Once you do this permutation, it is possible to get this square matrix which is non-zero determinant. Why is it possible to do so? Because otherwise the rank wouldn't have been, otherwise this matrix wouldn't have been full row rank. Because this matrix is full row rank, there will be a submatrix of size as many with as many columns as the number of rows, because it's full row rank, yeah, so that its determinant is non-zero. Yeah, I hope you're getting my point. Suppose, see, if there is a matrix like this, I am assuming full row rank, then I look at all possible such G by G matrices. This size is G cross Q. I look at all possible G by G matrices, yeah, so called maximal minors. I look at all such submatrices and their determinants, the maximal minors. If all of them are 0, then the rank cannot be G. That means the rows are linearly dependent on each other, right, if all of these submatrices have 0 determinant. So, therefore, at least one of them will be non-zero, just permute the columns so that that submatrix appears at the front, and you have P minus Q. Okay? Now, here is the interesting thing. When you have P minus Q like this, to obtain solutions that satisfy this system of equations, all you need to do is the following. First, put W2 equal to 0 and solve for P xi W1 equal to 0. That is what? Tell me. This is homogeneous part, right? The homogeneous part. And for particular solution, what do? You have P xi W1 is equal to Q xi W2, right? And notice that I can just look at this P inverse xi times Q xi. Such a thing exists because determinant of P is non-zero. This is a rational function matrix, and I can do a matrix version of partial fraction expansion to show that convolution integrals can be used to get a W1, a particular W1 hat, a particular W1 so that P xi W1 is equal to Q xi given W2 by convolution integral. That is how you solve. This is a transfer function matrix. That is it. So, in other words, for every W2 there is a solution. For all W2 in C infinity, there is a size Q minus G. There exists a W1 such that W1 W2 pair belongs to the behavior. Okay? Now, it turns out that using this idea, using this P minus Q partition and using the fact that for every W2 there is a W1, for every C infinity W2 there is a W1, we can now show that this result, which is true for autonomous, is true for these cases as well, right. This and something more is what we are going to see in the next lecture. Okay? Till then, take care of yourselves. Bye.